Thanks, Chris. You guys hear me okay? I think so. I'm going to try and tackle some big questions, some big ideas.
Before you go on, I might just turn that around. Just get that pointing upwards. How's that?
Even louder. I'm pretty loud as it is, but even louder. So some big questions. Big questions in physics, big ideas in physics. And as Chris alluded to, I want to tell you about how some of these big questions, things that we don't yet understand, that don't have an answer, are leading towards new technologies. Technologies that we think are going to have a big impact on society and a big impact over the course of your lives. So you may have noticed, if you were kind of falling asleep and having your eyes scan over what you see in front of you, you see a whole bunch of nice coloured, lolly-coloured pictures, various quantum physics devices that I'll tell you something about. But you might have noticed down the bottom as well a bunch of logos. One of the logos on the right-hand side you recognise as being one of the largest technology companies in the world. What's that doing there? This is a talk about fundamental physics, quantum mechanics. And yet we have one of the largest technology companies sitting off to the side there because they're sponsoring this research. Why are they sponsoring this research? What kind of a future does it have? What do we think we're going to see in the next 10 to 20 years in terms of technologies that are built from quantum mechanics? These are some of the questions that I want to tell you a little bit about today. I promised myself that I would keep it real. So everything that I'm going to tell you is true. There's no made-up version just for you. That means, though, that, to some extent, it's going to be a little bit challenging, a little bit mind-bending, but you've had all weekend long to roll around in the sun and your brain is now fresh and ready to soak up knowledge. So I've tried to meet that challenge. Hopefully there's some new and fresh ideas here, but they're not going to be easy. They're not going to be easy because they're real, because they're true, and because I haven't polished them up so that they're easy to digest. In fact, they're going to be rather the opposite. But bear with me. In terms of questions, I think it's going to be a better talk if you shout out your question. We can get carried away with that and we'll never leave here and you'll starve to death. But within reason, I'm happy with that, particularly if it's something around clarification. Hold on a second, I didn't really understand what you said. Can you say it again? Or can you say it a different way because I really want to follow? Let's have those style of questions rather than the kind of look at how much I know type questions. No one asked, that's right. Let's dive right in. Quantum mechanics. Who's heard of quantum mechanics? Who thinks that they know what it's really about? There was a lot of this. Good. People will tell you quantum mechanics is scary, it's hard, it's challenging, it's mind-bending. I think that that's true, but the question is why? Why is it so hard to understand? People say it's hard. If you meet somebody, in the street or in the park or something and they say they're a quantum physicist, you think, oh, that's impressive because it's really hard. But why is it hard? Anyone have any ideas on that? Shout it out. Why do you think it's hard? That always works really well. Forces break down at the quantum level. Anything else? Yeah.
Because it's so small, you can't really see it, and everything works slightly differently when it's at that really, really tiny scale.
Really tiny scale, things are different down at that level, and we can't even see the stuff. Yeah, what about up the back?
There's so many unknowns.
So many unknowns, yeah?
You can't make analogies to our physical world.
Can't make analogies to our physical world. Let's keep going, yep. Because it's new. Challenges our intuitive ideas of how reality operates. Humans find things hard when they can't put them in boxes. Yeah. I like it. So everything that you guys have said is totally true. And I wanted to do that because it gives me a sense of what you know and where your thinking is at. For those that maybe have not heard so much about it, let's do a brief introduction. What is this field about? What is quantum mechanics? Well, it's an area of physics that was developed over 100 years ago now. And it was developed by some of the smartest people who have ever lived. We know that because they invented quantum mechanics. They also invented relativity and a few other things. And they will play a leading role in some of the stories I want to tell you. But there's an important part that I've tried to capture in these slides, in these images. The birth of quantum mechanics happened by these guys sitting around, talking to one another, and writing things down on paper. They were aware of certain observations, certain experimental results, but the experimental results were few and far between. They were things like the nature of light, what was kind of known about the nature of light. They never dreamt, I think, that it would be possible one day in a lab only 50 meters from here, to do experiments on single, individual, controllable quantum systems, things like single electrons, single photons, single atoms. What they imagined were things that physicists call thought experiments. You can imagine Einstein there saying to Bohr, what would happen if I took an electron? And imagine that electron interacted with another electron. You know, when they would talk like this, that's a thought experiment. Imagine what would happen. What I'm going to show you is that those types of thought experiments, things that they wrote down in their notebook, things that they talked about over a coffee in 1925, are things that we can now do in a lab, and we can test those ideas, and nature has some surprises for us. Some surprises even to the founding fathers of the field. Let's have a look at some of those things. Quantum mechanics, of course, is it's the physics of electrons and atoms. It was originally conceived to try and understand the behavior of light and the behavior of atoms and behavior of electrons. And I want to show you a little video. I'm going to have a few of these throughout the talk that give you some kind of a picture. It's not a complete or real picture, but what you're looking at when you think about an atom. So that red, funny, spinny thing is an electron. And what you'll notice is that the periodic table there on the right-hand side, as you start to fill up the electron shells and keep adding more electrons, you see that there's some kind of cloud of charge of the electrons, and that there's some spatial arrangement to it. It takes on a particular shape. And it's quantum mechanics that tells us exactly what that shape is, exactly what that behavior of that electron cloud is. It tells us a lot more than that, but that's where we got started. So around the 20s and the 30s, people started to understand that matter, which is built from atoms, built from electrons in atoms, protons and neutrons in the nucleus, pile up to give us this periodic table, and quantum mechanics started to tell us about the detailed properties of that periodic table, tell us the detailed properties of materials, of stuff. In the 30s and the 40s, we started to use that knowledge to develop electronics, transistors, integrated circuits through the 50s and 60s, up to our modern age where we have computers, the internet, Facebook. These are things that, when you really get down to it, rest on our deep understanding, our fundamental knowledge of quantum physics. Without quantum physics, you can't build a transistor. In fact, you can't even build a regular solid, a piece of metal, and understand why a piece of copper conducts electricity. That's a quantum mechanical question. So this theory is incredibly important in devising and understanding the world around us and all of the technology in it, from lasers to superconductors. There has not been a single instance where a data point has disagreed with this theory of quantum mechanics. As far as we can tell, it is completely correct. That's not to say that in the future there might be an experiment that proves it wrong, but over the last 100 years, we're yet to find a single datum that disagrees with this theory. And it's an amazingly accurate theory as well, amazingly precise theory. So it's accurate, it agrees with data, it explains the world around us and lays the foundation for all of our technology. Think about that next time you log on to Facebook. I'm using quantum mechanics. One way you are. And yet, it's really hard to understand, and it doesn't make sense to human beings. Einstein was deeply troubled by this, and he said if quantum theory is correct, it signifies the end of physics as a science. He chose these words carefully there. I don't think he's just throwing up his hands and saying it's really hard to understand. I think he's saying something deeper than that. I think he's saying that reality is somehow built from some laws, some logic, some mathematics that maybe can't really be tested scientifically. I think that's what he's trying to say. He was starting to worry that our scientific method was coming undone when applied to this reality, this scale of the world, down at the level of quantum mechanics. Niels Bohr, one of the founding fathers, created the atom and other things, said everything we call real is made of things that cannot be regarded as real. What a strange philosophical comment to make. It's coming from a hard-nosed physicist who is somewhat allergic to philosophical ideas, and yet, confronted with quantum mechanics, starts talking like this, again like Einstein, up against not just data and ideas of how to make sense of the data, but questions relating to the real philosophical understanding of reality. Quantum mechanics brings us to that point. Richard Feynman, a little more pragmatic, but he still says if you think you understand quantum mechanics, you don't understand quantum mechanics. Pretty bright guy, deeply confused with quantum mechanics, as well one should be. Let's give it a go anyway, and I'm going to take you through a series of ideas, and I suspect that many of you have seen these before. I can tell you that for myself, I must have read or sat through lectures or watched something on these ideas many, many times. And it wasn't until much later, after seeing it many times, that I really started to think about it and really started to hurt my head about it. So even though these are things you've seen before, just because they're familiar concepts, try and dig a little deeper and really try and understand what's going on. Because then I think you'll come to this point of view to confront some of those hard questions. So let's begin with the familiar. We know that light can be, in some ways, regarded as a wave. That was the thinking at the time, over 100 years ago or so. It was a wave of electric and magnetic fields oscillating back and forth, moving out into space at the speed of light. But Einstein showed that, in fact, light can also be thought of as a particle. Whatever a particle is, whatever that is, it's some kind of discrete chunk of energy, a packet of energy. And then when it arrives and hits a piece of metal, it does so in a similar way to, we might think, a particle, some kind of ball. It's a simplification to say that, but yet it does behave in many ways like a chunk of something, a packet. What happened in the 20s was that people realized not just light, but matter can also be thought of as having this wave-like behavior and particle-like behavior. So wave-particle duality, that's a term that people use to describe in quantum mechanics how things like light and matter have these properties. And it's easy to say, and it's something that you've heard before. Yeah, I've heard light and matter behave like a wave and a particle. And, okay, but what does that really mean? It's a little more subtle than just something behaving like something else some of the time. You know, I talk differently to different people depending who I'm speaking to. But that's not what we're talking about. We're not talking about light having a different personality or a different tone of voice. We're talking about something much deeper. How is it that matter can have a wave-like nature? That's a very strange concept. What's the experimental evidence for that? Well, you can calculate using a computer the wave function. These are the shapes of those atomic orbitals. What happens when you put electrons in an atom and they start to pile up? They take on some kind of shape, and depending on the orbital configuration, you end up with bright spots and dark spots of something called the wave function. But you can see that it's certainly not a particle. It's something more hazy. Maybe we can call that a wave, maybe something in between. The test of wave-like behavior is just go to the beach or go to the swimming pool and you see plenty of waves. How do waves behave? The test of wave-like behavior is that we see a phenomenon called interference. Where does interference come from? What do you think? waves interacting, and if they interact such that the two peaks come together at the same time, we say they're in phase, and you have constructive interference. If a peak and trough come together at the same time, the same point in space, you have destructive interference. They cancel one another out. If you do that with light, light's a wave, you end up with bright spots and dark spots. The dark spots are where the peak of one of the waves and the trough of the other coincided. They cancelled one another out. You get a dark spot. You get a bright spot when they come together. So these types of patterns, interference patterns, are the signature of wave-like behavior. And you can see that, in fact, for atoms. You can see that for matter as well as for light. One of the other crazy things about quantum physics is not just that light and matter have this wave and particle-like behavior, but that when you try and make a measurement, something really weird happens. The first thing is you find out that nature is probabilistic, stochastic in some sense. It behaves more like rolling a dice, tossing a coin, than some deterministic law of nature. In other words, if you think of some light, maybe it's a laser beam, coming along this beam and hitting just an ordinary piece of glass, something like 4% is reflected, 96% is transmitted. You dial down the intensity of the laser to the level of a single photon, one at a time. Now you tell me, is that photon, this particular photon, is it going to be reflected or is it going to be transmitted? We can't say. All we can say is that it has 96% chance of being transmitted, 4% chance of being reflected. That's it. That's where the physics runs out. What about that particular photon coming along? Maybe it's got some property. Well, as far as we know, it doesn't. All photons are identical. And it's simply a statistical statement as to whether that photon is reflected or transmitted. So that non-deterministic, probabilistic aspect to quantum mechanics is going to be really important in trying to understand some of the other things that I want to show you. Einstein hated this. He thought that this didn't make any sense because it should be that the laws of physics, if I run them again and again, I should get the same answer. It shouldn't just be that I have a chance of getting a particular answer, a chance of getting a different answer. And he said, I'm convinced that God does not play dice. He was allergic to the idea that deep down everything is non-deterministic, probabilistic. What's the implications for that? It sounds okay when you're talking about photons hitting a glass or electrons, but we're built from electrons and atoms. Does that mean that your life is probabilistic? Or is it determined? As far as we can tell, the laws of nature allow for some kind of probabilistic interpretation. That's pretty weird. Let's bring it together. I want to show you this animation, and we might have to look at it twice. You've seen it before. It's sort of one of the foundational ways of introducing the bizarre properties of quantum mechanics. But there's so much here, actually. So let me go through it and point out some of the interesting aspects. The first thing is that we're going to do a classic experiment called a double slit experiment. And we're going to fire photons or electrons, it doesn't matter, matter or light, doesn't matter, through those two slits. And you see some of them bounce off, some of them go through. They make a pattern over there on the wall, on the screen or the wall. Wave-like properties are very different to that. If I have a source of waves on two slits, then those two slits act as sources of waves. But because they're spatially separated, over some distance, they interfere with one another, and I end up with an interference pattern on the back wall, those stripes. Quantum object, whatever that thing is, it's a bit like a particle, a bit like a wave. What's it doing? Now it's getting a bit weird. Okay, so it comes out, looks like a bit of a particle, spreads out in space like a wave, goes through both slits, interferes with itself, and then the most interesting bit, when it gets to the back screen, it instantaneously turns into a point. And if you do it lots of times, did you see what happened? You get an interference pattern. Let's make it even crazier. We put an eye, an observer, that can determine which slit the electron went through. And if you do that, what happens to the interference pattern? It's gone. If that doesn't freak you out, even though you've seen it before, then there's something wrong with you. You should give up. Why do I say that? I want to show you again because I think it's really important that we grasp some of those later parts. The most interesting bit there, yeah, go ahead. What would the observer be? Good question. Let's come on to that. What a crazy idea that I can put an eyeball next to the slit so that I can determine which slit the electron went through, and somehow that affects the outcome down the track. Is that like a tree falling in the forest? Let's come on to that. It's not so easy to just say a measurement device because I don't know what that really is. It's also made up of electrons and atoms. See what happens when it hits the back wall there? It's spread out in space, but where there's a bright spot, where there's an intense part of that wave, that's where I get a sudden appearance. But I still get that interference pattern built up. What an odd thing. We've got matter interfering with itself, matter being in two places at once, and now if I look at it, it's no longer in two places at once. If I look at it and I find it to be on the left, it is on the left. Have a think about some of the things I've just said. First of all, the world is probabilistic. It depends on whether you look at it or not. Go ahead. They could be photons, they could be electrons, they could be atoms. Yeah. How about people? Maybe they could be people. Why not? How about planets? Could they be planets? So let's see what happens on larger scales. I think that your question alludes to some other behavior for which we don't have a good explanation for yet, and I'll come to explain what that is a little bit. One of the things you saw going on there is an eyeball appeared. The point of the eyeball was to make a measurement meaning which slit did that quantum object go through. Can I determine that? If I can determine that, make a position measurement, then the wave-like nature disappears. It turns into a particle. I made a measurement. I asked the question, which slit are you going through? I get an answer, and in doing that, I see particle-like behavior. I could also ask a question about the wave-like nature. If I did that, I'd get an answer, maybe something like the wavelength. What's the wavelength? I'd get an answer. And the particle-like behavior would vanish. So here's a cartoon before the observation, whatever that means. I have a wave spread out in space and time, and then I make a measurement, I observe it, and all of a sudden it's localized. How to understand that? It's a deeply troubling philosophical concept. It implies that every time I make a measurement, there are two different outcomes that could occur with some probability. Some people think it's like if you make a decision to go and have a drink with somebody, or don't make a decision to have a drink with somebody, that at that point the universe divides, and in one universe you have a drink and in the other one you don't. And for every decision you make, the universe divides. That seems like a fair bit of extra baggage to have to invent in order to explain this behavior. Nevertheless, it's an interpretation of quantum mechanics. Let's come to this question that was asked before. How about larger objects? Somehow, we feel comfortable when we're talking about the weird, strange behavior of electrons and photons and atoms. But those laws should stay down there in the atomic realm, in the nanoscale realm. I don't want to think about things that I can pat, that meow at me, being in a superposition of different states. So the superposition we're talking about in the previous example is whether that electron or photon went through one slit or the other. When it's delocalized as a wave, it's going through both with some probability, with some amplitude. So Schrodinger's cat is something you've probably heard of, but again, it's one of those things that are often not really understood. You know it involves a cat in a box, but what is it really telling us? Why is it still around today? Why was this not solved? If you haven't heard of it, let me say what it is. The idea is you take a cat, you take some poison, a bottle of cyanide, and a hammer that's rigged up so that it smashes it and kills the cat, but then that hammer is wired to some switch, and the switch is thrown or not thrown by some quantum mechanical object. Whether an electron or a photon passes through one slit or the other, throws the switch or doesn't throw the switch, which releases the hammer or doesn't release the hammer, which releases the poison or doesn't release the poison, which kills the cat or doesn't kill the cat. And we just said that that electron can be in a superposition of both of those outcomes until I make a measurement, until I observe it. And while it's in that superposition, all the possible outcomes can coexist. So does that mean then that the cat is in a superposition of alive or dead so long as I don't open the box? Because opening the box would be a measurement, and then I'd see whether it was alive or dead. The act of measuring it would project it into being alive or dead. The point of this thought experiment is not to just give you an illustration of superposition. That's what most people think. Most people think, oh yeah, that's like saying you can be in two places at once or dead or alive at the same time. Yeah, that's part of it. It's trying to tell you something beyond that. It's trying to get at the idea that there's a disconnect between the microscopic world, the atomic world, and the macroscopic world in which we live in. We don't see cats in a superposition state. We don't experience nature that way. But yet, if I were to create an experiment like this, so that the microscopic influences the macroscopic, what's going to happen? That's the paradox, and that's what Schrodinger was trying to get at. There's something's not right here, because when I connect these two different worlds of different sizes, they're inconsistent. What do you think happens, by the way? Has anyone done this experiment? You can do it tonight at home. What do you think? Any ideas? Why don't you just do the experiment? Stop talking about it, do it. Can you do the experiment? Why not? It's interesting, isn't it? So some of the answers, why can't you do it? Oh, because you can't really get quantum particles into that configuration. Well, we can do that. What do you think? But that's true for the case of just the electron going through the two slits as well.
Like when you open the box, you're going to see the cat either alive, and there's no way that you can know that before you open the box it was in a superposition state.
So what if I do the experiment 100 times with 100 cats?
Never get it past 80%.
I might be able to learn something about that superposition state by measuring many outcomes. Yeah?
The cat can observe the experiment.
Oh. What if the cat observes the experiment, but no one observes the cat?
Could you have an external observer, like a camera?
So now we're really getting into some hard philosophical questions. What if the cat observes itself? Hang on. So long as the box is light tight and no information leaks out of the box, the cat can observe itself, but it's still in a superposition. Hang on. Isn't that... I mean, who's observing you? Is there a big eye in the sky if you look up? So where's the box in our universe? Do you see the problem here? You put the observer in the box and the observer out of the box, and you say an external observer, but where's that divide? So that's something called the measurement problem, as to where do I put the divide between a classical measurement apparatus, a classical observer, and I just say all that thing does is it measures the outcome of something, but it's not a quantum object. It can't be in a superposition. That seems artificial.
So, if the cat is in dead superposition state, it can't work itself, so it must be alive.
Well, it's in a superposition of thinking that and not thinking that. We get ourselves into some pretty weird questions and trouble philosophically thinking along these lines. And you might think that in some ways this is a bit of a beat up. Is the world really like that? Do scientists think that way? Are experiments being done in laboratories around the world to actually probe this stuff? It seems like the kind of thing that's nice to read in a book or see in a film, but I hate to tell you, but we don't understand quantum mechanics. And we are doing experiments to try and understand better what is going on. It's a deep mystery. Here's an object that you can see with your eye. It's not large, 60 micrometers, but that's visible with your eye. It looks like a speck. A few years ago, that object, it looks like a tuning fork, that's basically what it is, was shown to be in a superposition of states. Okay, so we're not talking about an electron or a photon or an atom anymore. We're talking about an object large enough that you can see with your own eye. And yet, if you cool that thing down and do experiments on it, you can show that indeed it can be in this superposition of states. There's no law that we know that just turns off as you scale up to larger objects, turns off the quantum mechanics. It's not like the superposition stuff and the measurement weirdness lives down there and we live up here and there's some kind of divide between the two. As far as we know, that divide doesn't exist. It's an artificial divide. Yep. Yeah, so the superposition can mean many different things, and why don't I come on to that? Let me come on to that right now. One of the challenges for superposition, and I'll say a little more about exactly what it is in a moment, is that this act of measurement can be more than just a human eyeball. It can be a means of extracting information about the system. The environment can do that. What does it mean the environment can measure something? That seems strange. Well, if you interact with the environment, whether that environment is an eyeball or a brain or a ruler or electrometer or whatever it is, some of the details of your state get mixed up in the details of your environment. And we call that decoherence. It doesn't actually solve the measurement problem. It just says that the world's even more complicated. It says that it's really hard to create that box with that kitten in it and have it not interact with the outside world. Some information leaks in and out of the box. It's really hard to make it light tight so it doesn't conduct any heat, so magnetic fields don't penetrate, gravity doesn't penetrate. It's harder and harder. Those interactions actually lead to an effective measurement of the system. Yeah?
So you're saying that measurement is the same as interaction?
In a way, yes. I am saying that in a way. Yeah. Let's look a little more about superposition. So superposition can be two places at once, but it can also be two different energies at once. So here's an atom in its ground and excited state. Here's an atom where it's in two different places at once. And we can talk about a superposition of being on the left or the right, or in the ground or the excited. We can talk about something called the spin of the electron. We can have a superposition of that state as well. Okay, so any kind of variable in quantum mechanics you can think of as having a combination of those two things happening at the same time. So here, the energy state of the atom, that's its excited state and ground state, I can actually have a superposition of both of those. It's possible to put an atom into that state, but if you make a measurement, guess what? You only measure one outcome. It's not like the measurement shows you that both are happening at the same time. You only see the ground or the excited state. Yeah. Yeah.
How did you conduct that experiment?
So how could you conduct an experiment to create a superposition in the first place? That would require you to not have an observer. And that's exactly right. You need to create an environment or a situation in which the environment hardly interacts with the atom. And on a short enough time scale, if that environmental interaction is weak enough, then those superpositions can exist. This is what you end up seeing. This is a measurement now of the probability of finding that atom in its ground or excited state. And we're actually driving it with some radio waves, making it oscillate from its ground to excited state. But those other electrons and atoms coming in here are meant to be some environmental interaction. And what that does is it kills this coherent superposition of those states. It makes a measurement. An atom comes along, it interacts with that atom, and in doing so, it ends up in the ground or excited state rather than a superposition of the two. Yeah.
You need to not have an observer to know that it exists in two different states. So if you have an observer like this one outcome, how do you know that it exists in two different states?
Yeah. Yeah. So that's an excellent question. If you can't measure the thing, then how can you conclude anything about this superposition? Nobody was watching while it was in a superposition. So what you have to do is create a situation where, rather than an equal superposition, I can somehow have a variable superposition. Maybe it's not 50-50 mixture of ground and excited state. Maybe I start off saying it's 90% the ground state, 10% the excited state, a little bit of that superposition. Let me prepare that state, then make a measurement. I'll get an outcome. It'll be ground or excited. Let me do it again. Measure the outcome, ground or excited. Do that over and over and over. And what I should find is that the probability of measuring the ground or the excited state reflects that superposition. If it's in an equal superposition of both states and I measure it over and over and over, then I get 50% in one state, 50% in the other state. So we are deducing something about the superposition state based on the measurement outcomes, but the key is you have to do it many, many times in order to learn that probability. You're right that if you make a single measurement, it doesn't tell you anything about the superposition. Yeah? How does it know that it's been observed? We're getting into trouble because we're now projecting feelings onto quantum objects. But then you're made up of them too, and you probably have feelings. I want to say it doesn't know. I want to say that one of the fundamental principles of quantum mechanics is that the act of a measurement gives us an answer and leaves the quantum system in the state that we measured. Beyond that, we can talk about what that means philosophically, but that's the statement quantum mechanically. Yeah, let's take two more and then we'll move on. Yeah. How do you know it's right? Yeah, good question. How do you know it's right? Well, as I said at the beginning, it's a theory, but it's one that agrees with data, and there is no data that disagrees with it, and we've been taking a lot of data for a long time, and it's very successful. So, as much as I can know anything in science, it's a pretty successful explanation of the world. Yeah.
So quantum mechanics is all about statistics.
Yeah, that's true, but I want to say something more profound, and that is not just quantum mechanics, but the world in which you live and what you're made up of at its most fundamental level is statistical. Yeah.
So
One more.
Does that mean that at one time, at one moment, the measurement is taken from one observer on one atom or something, then it's in one state, but then in the next moment it will be in the other state, so that the next measurement can be different?
The next measurement can be different, but once you make a measurement, if you measure an atom and you find it's in the excited state, after that measurement, it's in the excited state. It's no longer in a superposition. So in measuring it, it is what you measured. It's not like it suddenly can be something else.
So if you conduct trials, so trial 1, you find it to be in the excited state, then that means that in trial 2, perhaps 10 seconds after you've done the first trial, then it will be in the excited state.
Right.
from that observer.
That's right. So you saw when those red balls went through the double slit, when there was an eye there, it made a measurement that it was on the left slit. At that point, it was on the left slit, and it has to then propagate out from that slit. Okay. Let's move on. It's going to get even weirder, I'm afraid. It's been pretty strange already. Just have a brief recap of some of the crazy stuff we've started to think about. The world is statistical, non-deterministic. Your future is not written quantum mechanically. There's some role for an observer that measurement is something very strange in quantum mechanics. There are superpositions of states, energies, position. Let's get even crazier. When you have more than one particle, everything we've been talking about so far is really the physics, the quantum physics of a single particle, single electron, a single photon. When you have interactions between particles, certain types of interactions, you can have an effect that is really strange, something called quantum entanglement. This effect, this phenomena was proposed, it was sort of invented by these three guys, Einstein, Podolsky, and Rosen. And the reason for their idea, the reason they conceived of this experiment, or this kind of thought experiment, is because they thought that it might be a good way of showing that quantum mechanics is ridiculous. So given the rules that we've talked about of measurement and superposition, they thought, okay, if you apply those rules to particles that are interacting, then we can show that it gives you absolutely ridiculous outcomes. So it was a way of showing that the theory must be wrong. Turns out, though, if you do the experiment, just because you don't like it, doesn't mean that nature is going to listen to you. Turns out that that's exactly what nature does. Let's have a look at what I'm talking about. I'm into some really tricky territory because I'm trying to explain something now for which there is no analog in the classical macroscopic world. The superposition stuff, we can talk about waves, and we can think about waves at the beach, and there's constructive and destructive interference. That's something that we're pretty familiar with. Now when I'm talking about entanglement, I can't give you an analogy. So I really am going to have to kind of polish it a little bit, smooth over some of the details. But nevertheless, I think you'll get the essence of what I'm saying. To really do it properly, we have to write down mathematically what's going on. It's not that we can't describe it. We can. It's just hard to explain with an analogy. But let me try an analogy with coins. Okay, so I have a 50-cent piece, and I toss it. And what happens? If it's a good coin, then I get 50% heads and 50% tails. No problem. Let's get two pairs of coins. Classically, that means the physics of Newton and the physics before 1900 or so. I've got two pairs of coins. Maybe you have one coin and I have the other. That would be one pair, wouldn't it? Okay, you toss your coins, I toss my coins. What do I see? Well, on the left, I get roughly half the time heads, roughly half the time tails. And on the right, I get the same. Coin one, this one's heads. On the right-hand side, tails. Coin two, tails, heads. Coin three, heads, heads. Tails, 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 heads, whatever. You toss some coins over there, I toss some coins over here. 50% of the time you get heads, 50% of the time I get heads, no problem. Let's imagine those coins are entangled, quantum mechanically. They share a state irrespective of the separation between the particles. They are still in some ways a single state. What happens is, if I take entangled coins and I toss my coin, I get heads. You toss your coin, you get tails. Now imagine we keep doing that experiment and you find every time I toss a coin, you get the opposite answer. Imagine you only have these coins though. You're outside doing the experiment. What happens? You toss coins, you 50% of the time get heads, 50% of the time get tails. You come inside and you say, well, that was really a letdown. He sent me outside to toss a coin. I did it. I got 50% of the time heads, 50% tails. Big deal. But it's not until we then compare your results to my results that you notice every time I had a head, you had a tail. Every time I had a tail, you had a head. Why is this so crazy? Well, it's perhaps not mind-bending to think that there might be connections and correlations between things. You know, if you put your hand in your bag and find that your keys are not there, and you instantaneously realize that they're at home on the table, that's not surprising. It's a correlation. You can infer information about where your keys must be based on a measurement here. Yes? Yeah, so there's a good question. Doesn't this violate relativity? You're implying that if I made a measurement here, then instantaneously I've transmitted that to this other side. Well, so it turns out that you're right on the edge of people thought this way for a long time. But it turns out that nature is a little bit clever, and you can't use it to transmit information. If I give you a coin, you go outside and you toss it, and I toss mine, how can I transmit information to you? It's only when we bring them back together, or you get on the phone, you call me and you say, coin 3's a head. And I say, yeah, it's a tail. Ah, okay, but we had to speak, we had to transmit information at the speed of light in order to see those correlations. Otherwise, they're there, but transmitting information is not allowed. What's really crazy about this is the part I haven't said. Do you remember we talked before that the world is statistical? That photon coming along, hitting the glass, 96% chance of being transmitted, 4% chance of being reflected, but I couldn't tell you exactly the outcome for a particular photon. And I said that that was it. There was no other law underneath it. It's just statistics. Okay, it's the same here. I can't tell you the outcome of coin 4. I can just tell you it has 50-50 chance. But nevertheless, over on this side, it also has 50-50 chance, but they're opposite. That's a bit weird. The world is non-deterministic and yet non-local. These statistical aspects link things across space and time that is vast. That's strange. What's it good for? Well, might be good for voodoo, I don't know. It's a little bit like that. Isn't that kind of crazy? I stick a pin in a doll, you feel a pain somewhere no matter where you are. It could be on the other side of the universe. You know, people thought that this is proof of some pretty weird stuff. Maybe this is, I don't know, telekinesis. Maybe this is some way of transmitting my thoughts to my friend, even though they're in another country. And it was all the rage in the 60s and 70s, and even pretty recently. Turns out in this movie, if you've seen it, it's ridiculous. There's an observer, and the observer allows you to determine how your day is going to be because you can project it into something. It's rubbish, but you know, don't be distracted by what's on the internet. You guys believe everything you read on the internet, right? What's it good for? Well, it turns out that those properties, the properties of entangled particles, if you make a measurement of one of them, then you affect the outcome of the other. You affect the measurement outcome of the other. So if I have entangled photons, I can actually see if those photons have been measured or not, because it affects those outcomes. And that's a way of seeing whether information you're transmitting, for instance, on a fiber optic cable, has been intercepted, eavesdropped by somebody, and measured. I can see that it's been measured because I can use entangled pairs of photons to encode the information. That spooky effect is already showing up today. You can buy products that allow for secure communication. It's not secure because it transmits it in a way that nobody can possibly get to it. It's secure because if they get to it, quantum mechanics allows you to know that that has happened. And so you can throw away that information and keep trying until you know for sure, quantum mechanically, by the laws of physics, that that information was not measured by someone else. Everything I've shown you today, thus far, really, has been a drawing, a cartoon, a nice animation. I really want to make a point. As you sit there and see these things, and you sit in classes at school, you read textbooks, you look at YouTube videos, and you see nice drawings, nice cartoons on electron does this and a wave does that, and the measurement outcomes. How about real experiments? Can you actually really measure those things, or are they just sort of drawings? It's one thing to draw something and conceive the idea. Can we actually test it in a lab? What does it take to do that? Is there any point in doing it? What do you think? Maybe we should stop with the nice animations. They look good. That's convincing. Do we have to do any experiments? Should someone actually make a real device and try and measure this? Yes? Why? Why do you think? To confirm it? Yeah, those animations are based on human beings' brains. They're based on mathematics as well, but we have to see whether we're right. More than that, often in doing experiments, nature reveals much more than we anticipated. I think it's pretty interesting. You can go back and look at, again, the founding fathers of the field proposing these types of ideas, but can we really do experiments? How would you construct an experiment? How do you construct technologies to operate according to these bizarre rules? How would you do an experiment anyway? What would it take? Well, the first thing is, in order to do an experiment in quantum physics, you're going to have to play with matter and light down at this level here. Because up at the macroscopic level of plants and tables and people and all that stuff, you don't see much of this superposition stuff. You don't see the wave-like nature of matter. Why is that? Well, we said before that the environment has something to do with it. The environment's making measurements, and as things get larger, for various reasons, they start to behave classically because the environment is making a lot of measurements. Down there at the quantum realm, at the nanoscale, it's possible to isolate objects, create superpositions, and keep those superpositions alive for a much longer time. So the challenge then, if you want to do experiments in quantum physics, is you have to be able to make structures that are nano-sized. Why nano in order to see quantum effects? Well, one of the reasons is that if you look at what happens when you take an electron and you put it in a small nanoscale box, then you start to see its wave properties. So there's an electron now confined by the potential energy of some kind of box. If the dimensions of that box are comparable to its wavelength, the electron wavelength, or the atom's wavelength, then you start to see wave-like behavior. If you make the box really big, compared to the wavelength, then you start to see classical behavior. So in order to do these experiments, we need small structures to reveal the wave-like nature, and we have to decouple them from the environment so that there are no measurements happening all the time. They're the two kind of requirements. You might have noticed there also that there was an energy scale associated with those different wave aspects of the electron. I'm going to come on to that in a moment. Okay, so we're kind of moving a bit quicker now. We've thought deeply about quantum physics, and what I'm trying to tell you now is that there's a way of doing experiments in quantum physics, and the way to do it is to hijack the semiconductor industry. What a strange idea. Hijack the semiconductor industry so you can do quantum physics experiments. Well, the reason is these guys have been at it for some years, miniaturizing electronics, shrinking down transistors to the smallest scale. Look at the size of transistors as a function of the years going by. 2010, we're down at something like 35 nanometer, and today we're down to 18 nanometer, 14 nanometer. That's the size of the gate in the transistor. In other words, it's possible, using the techniques that are used to create integrated circuits, to make structures and make devices that are nanometer scale. That's a perfect playground to start to do quantum physics experiments. And that's exactly what we're doing. I want to turn now to tell you specifically about some of the things going on in my own research group here at the University of Sydney. We start with some extremely clean materials. Materials that are grown atomic layer by atomic layer using a machine called molecular beam epitaxy. Okay, so that machine there, it's a lot of stainless steel. Deep inside it is a vacuum unlike anything else on Earth, and allows you to grow one atomic layer at a time a very pristine, clean material, a semiconductor. And it's that semiconductor that we're going to use as our kind of platform to do quantum physics experiments. I'm trying to give you a sense now of what real experiments look like and what they take in order to be able to play in this game. You start with that clean material. You've got to do more than that. You have to pattern it. What does pattern it mean? It means remove little parts of it and start to shape it into a configuration that allows you to do what you want to do in the experiment. So techniques of nanofabrication, of lithography are used. Clean rooms, people dressing up in bunny suits. Why do they do that? Avoid contamination. Okay, who's contaminating who? Is it to protect you? It's to protect those nanoscale devices, those tiny electronic features, from the filthy, dirty people that you are. It's true. You know what dust is? Ask your friends. Do you know how big dust is compared to the size of these? Pretty big. Here's a device that we made a couple of years ago. You might be able to make out some detail there on the chip. If we zoom up on that, you can see a little more. These are connections and wires that are created using lithography techniques that are needed to make integrated circuits. Is that a question? Yeah, so there's a challenge to interface those quantum circuits down there at the nanoscale with their... How are we going to actually do an experiment? We're not that size. So there's an interface problem, a way of connecting the macroscopic world to the micro. And I'll show you how we do that. In fact, you're looking at it right now. Zooming in, you'll see that there are connections here. They're actually electrical connections that start from the outside, from the world we live in, wires and things, and bring those signals down smaller and smaller. To change color, I had to change microscope because there's not one microscope that allows you to cross all of these dimensions. We're still with an optical microscope at the moment as we zoom up. And then eventually we have to cross onto an electron microscope. There's the scale bar, 1/1,000,000th of a meter. So what you're looking at there are metal structures on the surface of a semiconductor. Those things are 10 nanometers or so across. And what we do is we put the negative terminal of a battery connected to those metal structures. It creates a negative electric field, and you know electrons are negatively charged. If you do that, you trap electrons in these regions. It makes a small single electron trap inside a semiconductor device. If you're wondering whether that's what electrons look like, no, they're blue circles that I drew on PowerPoint because I can't draw electrons, but you knew that. Okay, now you've made the device. How are you going to measure it? Remember what we need to do. We need to isolate it from its environment. We need to isolate it from its environment, otherwise the environment is going to make an observation, make a measurement. The other thing is, the energy scale associated with that wave-like property, that energy is very small. It's much smaller than the thermal energy at room temperature. So if you put your hand on your forehead, you feel it's warm. What are you feeling? You're feeling the jostling of atoms. Their thermal energy, if you think of atoms connected by springs, it's kind of what's going on. They're moving and jostling about with thermal energy. We have to slow down that jostling motion, slow it down till those atoms almost stop, so that their thermal energy is much less than the energy associated with the confinement. To do that, you have to cool the thing, the integrated circuit that you've made, you have to cool it down to temperatures very close to absolute zero. 50 meters from here, we're cooling devices below 10 millikelvin. How cold is that in Celsius? Minus 273.14. Colder than that. Let me get a little bit technical to finish up, because I know that some of you have thought about these concepts for some time. I want to show you really what it looks like to do an experiment in this area, in this field. I want to show you that the concepts that we've been talking about are not just the realm of YouTube cartoons and drawings, but are really happening in laboratories. So let me get a little bit detailed just for a second, and then we'll finish it up. What you're seeing here on the left is a sandwich of different semiconductors. It was grown using that big stainless steel tool that I showed you. The important and interesting part is that red line. That red line is actually a two-dimensional plane of electrons. It's trapped between two different types of semiconductor. So think of that red line there coming out at you, out of the screen, as a 2D sheet. On the top of the semiconductor are those metal features that I showed you, those tiny little wires. We connect them to the negative terminal of a battery, make them negatively charged. And what they do when they're negatively charged is they deplete the electrons underneath them. So think on the top here, there are metal, fine metallic features, I'm going to call them gates. Negative voltage on those gates. It removes the electrons in the 2D sheet. What's really cool about this is that depending on what you want to create, what kind of shape, you can change and dial up and down the voltages on those gates, and therefore shape the confining potential of the electrons underneath. No voltages on the gates, it's just a two-dimensional sheet. Put voltages on the gates and you start to create a weird potential to confine single electrons. This is what it looks like if you're staring down an electron microscope onto the top of this device. Okay, so I end up with electrons. I'm going to shade them blue now instead of red. Electrons everywhere those gates, I've artificially colored them, but they're metal gates. Wherever they are, there aren't any negatively charged electrons underneath. Does it make sense? How do you measure single electrons? How do you make a measurement of whether an electron is there or not? Let's get a little bit more technical, because I think that you'll follow it no problem. Over here, I've created a puddle of electrons. I've labeled the number of electrons n. I don't know how many are there, maybe 100. That thing is called a quantum dot. It's a puddle, a confined region of electrons. Off to the side, if you see this, there's a big puddle here, and then a small little constriction, a little neck. Why is there a neck there? Well, because I've got a negative voltage on this gate and a negative voltage on that gate, and they nearly pinch off that little neck. If you measure the resistance, the electrical resistance through this path, the value that you get depends on the width of that neck. If that neck changes, gets wider, the resistance changes. The resistance goes down. There's more electrons to carry the current. The width of the neck depends on how much negative charge lives over here. One electron jumps out, the width of the neck gets larger. One electron comes in, gets smaller. You see that? Okay, now you know how to do this experiment. You want to count single electrons, you need to measure the resistance of a nearby constriction. So there you go, some data we took a month ago. I photographed it with my iPhone on a regular oscilloscope because I want to show you how real this is. What you're seeing single electrons being counted one by one, making a measurement. We had a cartoon with an eyeball making a measurement of whether there was an electron here or an electron there. Now I'm showing you an experiment with real data where it's possible to do those experiments. Yes? Where were they? Oh, why electrons, not atoms or photons? Is that what you mean? Yeah, so the electrons, we can put them in there just by connecting any of these regions of the semiconductor to a voltage source or a current source, and then drag electrons in from the battery. You might ask the question, why electrons? It turns out that, as I said before, that the kind of semiconductor industry has given us the tools to make integrated circuits that steer currents around. What we're doing is taking that one step further into the realm of single electrons, where you can start to probe their quantum mechanical behavior. And there you see it. I'm going to go one step further. We can actually take electrons and make not just puddles of them, but push down to the limit where you have single electrons and control the configuration and interaction between those electrons. It's almost like creating a molecule artificially inside a semiconductor. Imagine if you had a molecule, but you said, I don't like the bonds. I don't like the bond strength between those two atoms. I'm going to tune it. I'm going to do that in the lab with a voltage. You can do that here. Those numbers you see in this diagram, they correspond to literally the number of electrons in this double quantum dot structure. So this 0, 1 means there's no electron on the left, there's one electron on the right. 0, 2 means two electrons on the right. 1, 1 means an electron in each one of those two wells. If you want to change the coupling between the wells, you can change the voltages on those green gates. Isolate them, bring them together, create totally artificial molecules inside a solid-state system. I won't go into the details. Our objective in doing this is to encode information quantum mechanically in the state of these electrons, to create superpositions, just like what you saw in the YouTube cartoon. There is an oscillation in the probability of the ground and excited state. So 1 means it's totally in the excited state, 0 means it's totally in the ground state. We can create combinations of those two, superposition states. And it's this physics that actually led to a Nobel Prize 3 years ago, to Serge Haroche and Dave Wineland for pioneering some of these ideas of controlling single quantum systems. What does the future look like? That's where we are today. Over the last few years, we've been working hard to try and scale up these experiments, to go beyond just controlling single electrons, but start to control arrays of them. What about 2D arrays? Ultimately, where we want to go is to be able to control millions of them, encode quantum information into the states of those electrons, manipulate that information on a very large scale. But it's fair to say that this field is actually in its infancy. It's been waiting for you guys to come along, finish school, to enroll in university, to get degrees, and start to pioneer work in this area. If you look around the world today, you see experiments in quantum physics that look like this. This one up here is manipulating the quantum properties of diamond, of spin states inside diamonds. Down here, it's ions and atoms controlled using microwaves and optical techniques. And in my own lab here, it's the spin state of single electrons in semiconductors. But if you squint a little bit, and I fade the color a little bit, you could be forgiven for thinking that what you're really looking at is not so different from where computers were at in the 40s. It's quite true. Where this field is at today is somewhere before even the creation of the world's first computers. We're really at an early stage of this technology. I think that makes it exciting. Exciting to imagine what we could build, what that technology would be good for. What does it give us that we can't do today? How are we going to use those weird and strange properties of quantum physics to do something that would otherwise be really challenging to do with classical objects? That's the big questions. We already have some sense of what that kind of quantum technology would be good for. We know that it gives us tremendous power with certain types of problems for computing. We can solve certain types of problems with a machine built from quantum mechanical principles that would be very hard with a classical computer, even if it were a supercomputer. We know that we can make sensors that can detect extremely weak magnetic fields and electrical fields, gravitational fields using quantum mechanics. We know that we can simulate other quantum mechanical systems. So we can design drugs, for instance, or maybe molecules that are needed to make processes like the generation of fertilizer much more efficient, to devise molecules that are going to be useful for carbon capture. Some of the big societal challenges that face our world are going to need technology that can help us design and construct those solutions. That's where we want to go. That's where we're going to go over the coming decades. Within your lifetime, I think you're going to see this technology emerge from where it is today, something like this, into a fully integrated platform, scaled up to millions of qubits. The challenge, of course, is one that's happening on a world stage. It's not just happening here, all around the world. And as Chris said at the introduction, we're about to move into a beautiful new facility that's been purpose-built with all of the specifications that you need to do experiments at the nanoscale. Experiments in quantum physics where you can really take the environment, that big eyeball, and push it further and further away. That eyeball shows up in many ways, in the vibration of the building, in electromagnetic interference, in fluctuations of the temperature. All of those environmental influences, they perturb that quantum system. That makes it very challenging to do these experiments. You need a purpose-built special facility where you've thought deeply about all of those aspects. That's something that's coming online in a month, just in time for you guys to be doing experiments there with real quantum systems, not just the kind that you see on YouTube and Facebook. So let me finish there and take some more questions. Thanks.